over the longitudinal strain. Sorry. So as it gets stretched outwards and gets pulled inwards, how material reacts to that becomes of some importance, or could. Slowly the markers are moved here. So let's go through an example. Lost one other thing, negative. Because typically transverse strain is a negative number, so the extra negative there cancels that negative out. All right, so I have, let's assume infinite significance there, long steel beam, and since I wanted a specific value, I looked this one up, 8E. Now I do not know what particular makes this particular steel special, other than probably its own unique carbon percentage, but that's the specs for it in case you feel like looking it up. What I do know is that Young's modulus is 6.89 times 10 to the 10th units. Didn't talk about it before, but I've laid out enough information. What are the units of Young's modulus?
Pascals.
Is that from memory?
That's from memory. I guess times 10 to the in engineering notation that would be giga. So would it be 68.9
times 10 to the 9th? Or it's 68.9 gigapascals.
Okay, so 68.9 G.
All right, so other than his memory, how would you figure it out?
But
Figure out that it's possible.
I would probably just look it up online.
Oh, you can do it that way too.
Or look into the textbook.
All right, so let's go back then. Such an engineering approach to it.
I think if I remember, strain is related to pressure.
Stress is closer to pressure, but there are some differences between the two. So let's look back at our stress strain diagram here in the elastic region. Young's modulus is the slope here. I use a dollar sign for slope instead of M, just because we use M for too many other things. So this is slope. Usually not with a T. All right, slope. How do you find slope?
Rise over change in Y over change in.
All right, in our case, change in sigma over the change in epsilon. So this is stress here. What are the units of stress?
Newtons per square meter.
Yeah. So that's a Newton per square meter on top. And what are the units of strain?
Change in length over change in, what was that, radius?
That was an L sub 0.
Oh,
That's where you're looking. Looking for units here.
Meters. But it's not like
meters?
It is not meters.
no.
It shouldn't be Newton, it's not Newtons, is
It
it?
is, you are correct, it is not Newtons. Let's go through an example then. I have a bar here that I pull out. Let's say it's a 5 meter long bar, and I pull on it and I stretch it out to, so let's make the length now 5.2 meters. Assume it stays in in fact, it doesn't matter if it's in the plastic or elastic region here, but what is the strain?
Be the difference of the 2 divided by 5.
Okay,
My calculator's broken.
One
Not
divided by
broken,
five.
it's
you can handle, pardon?
Yeah, it's just 1 divided by 5, it's,
So 0.2 divided by, 0.2 what?
meters,
Divided by 5 what?
meters.
That's the way I'm thinking.
0.04 meters.
Okay.
0.4,
Are you thinking of something or you're stopping?
yes. Yeah.
Meters cancel out.
0.04 what?
I just said value.
No, yeah, it's,
0.4,
the units cancel out.
right,
Yeah.
It's just 0.04.
yeah.
Oh, okay.
Yeah, stopping was the right choice.
Oh, it's unitless.
It is unitless.
Oh, okay.
Or if you really have this strong desire because of some childhood scars to write units, meters per meter also works. But it's unitless. So that leaves us with the units of Young's modulus as newtons per square meter, which is by definition a Pascal. Thus the physics joke of Newton, Pascal, and Einstein were playing hide and seek. Einstein was it, so he had his eyes closed. Pascal went off running around, trying to find a place to hide. Newton stood right behind Einstein and drew a 1 meter by 1 meter square, stood right in it. Einstein says, ready or not, here I come, turns around and says, Newton, I got you. Newton says, no, you didn't. I'm a Newton over a square meter, you call it Pascal.
Oh, I get it now.
Like most physics humor, you're laughing very loudly on the inside.
I was more worried I wasn't gonna get it.
What about halfway in? And I'm like,
All right, so Young's modulus, units of Pascal, so that's where we were right here.
Yeah.
Yield strength. Yield strength is 2.16 times 10 to the 9th Pascal. Ultimate strength is just specs that I looked up. 2.43.
What was that, UIT? Ultimate, oh.
ULT.
Yeah.
Let's see. It's how many oh, okay. 20.
Let's see, I'm going to give you another piece of information here. Diameter, I didn't give you. That's a decimal point there. So the diameter, just so, is 1 centimeter. And the force is 100 kilonewtons. Now we are going to assume some ideals here that, well, I'll talk a little bit about why the ideal is not reality when we come up with an answer. So first, let's establish have we entered into the plastic deformation? Or are we still in the elastic zone?
Looks like we're still in elastic.
All right, let's back that up with some numbers.
Because that's because the Young's modulus is 68.9 gigapascals. That's the yield is, that sigma yield is 2.16 gigapascals, and sigma ultimate is 2.43 gigapascals.
There seems like there was another thing that was, I was thinking that there was something missing there.
Wait, am I right with,
Oh,
concerning the information I gave, or?
no, the numbers you gave are right, but what actually is the stress being applied? These are set for the material, whether something is applied or not, but we need to actually figure out what is the stress applied.
Oh,
So-
I don't-
What's the formula for stress?
Force over area.
What's the force?
100,000.
What is the area? I actually didn't write the shape of it. A rod. Pretty sure that's what I did in here. Yes.
Wouldn't 1 times 10 to the 5 be 10 kilonewtons?
Wouldn't,
No, kilo is a 1,000, which is 3 zeros.
Oh,
wouldn't we have to,
5 zeros don't.
we would have to find the area, because we got the length of it and we got the diameter.
Yep, so how do we find the area?
Area of a cylinder.
Yep.
Well, the cross-sectional area is pi squared.
Okay, yeah, thank you for the clarification there. Yeah, cross-sectional area. Yeah, definitely not surface area.
Okay, okay. Thank you.
That's pi times what's my radius?
3.14.
Or 0.005 meters.
Oh, whoops.
7.854.
7.851, 54.
Meters squared. For the cross-sectional area. I know.
Something's way off on that one.
Yeah.
Oh, no, excuse me, I forgot the e to the negative 5.
Yeah.
Yeah. Meters squared.
Okay. Yeah, it hadn't been square meters, that's on the big side. All right, so we have the area now, we can plot that into here. And so we end up with the stress that's being applied. It's 1 point something.
On 27, 273.
273?
Yes.
Times 10 to the 9th?
Yes.
Okay. Pascals. We have not exceeded the yield strength, so we are still in the elastic region. So that's how we do it.
Oh, I didn't. Just. There we go. Yes.
Since I know the stress now and I'm in the elastic region, so again, we're looking at our stress strain. 1.273 gigapascals. What is the strain? I know the slope of the line.
Let's see. Rise if I run. So that's the rise. So it would you'd multiply that by by the rise to get to run.
Wait, I missed,
Rise divided by run equals the slope.
okay,
So we know the slope.
alright, so we know the slope.
So we would, we would multiply both. I think we multiply both sides by the slope to get.
That wouldn't do it.
Uh,
Alright, so what is the rise is what we just figured out. So I have 1.273 times 10 to the 9th pascals divided by my strain is equal to 6.89 times 10 to the 10th pascals. We can simplify the math some. If I divide both sides by 1 billion, divide by 10 to the 9th, then this reduces down to 1.273 over epsilon is equal to 68.9. Just to make numbers easier to work with. How do you solve for epsilon?
You multiply 68.9 by 1.273.
Nope.
Isn't there a rule that you can swap the denominator?
Yeah, you divide.
Yeah, you divide.
Oh,
Divide the 1.273 times 10 to, divide the 1.273 times 10 to the 9th by 6.89 times 10 to the 10th.
All right, so I can say anything over 1, and now I'm just cross multiplying, so this diagonal equals that diagonal. Commutative property holds, so I can just flip across the diagonal. And so 1.273 divided by 68.9 is equal to my strain. And it's
0.0185.
0.0185.
Yes.
You about to say something?
I'm not sure yet. Hold
Okay. Do we need a dramatic pause for thought?
on. Wouldn't that be? That would be. Never mind. This unit was such on.
Okay.
I was thinking of a unit, but.
I do appreciate that. Doing classes, I have people not even thinking about units, they just want to throw the number down and they're done. Recognize leaving off units when units need to be there on a test or quiz and your final, you don't have to track units as you go, but you need a unit on the final answer. If you leave units off and there should be a unit, that's on a 10-point problem, that's -3. It's 30% right there. And I have some people who just habitual leaving units off. All right, so how much did this thing actually stretch?
We'd use the strain formula to find the delta L.
Yep. So what is, the strain is delta L over the initial length.
Yes.
So 1.185 is equal to.
Wait, 185.
Yeah.
Meters.
All right. Now, all that's standard stuff when you're starting out on this stuff. All right, so now let's get to Poisson's ratio. As I pull this thing out, I am not creating any matter. So I'm assuming that the volume stays constant. That's a questionable assumption. But we assume that it stays constant. So the initial volume is equal to the final volume. It's a cylinder. What's the formula for the volume of a cylinder?
R squared times the length.
So this is pi r squared times the length, the initial radius length. And this will be pi r final. Well, I know r sub naught because that's given in the problem, or it's close enough. L sub naught's given, so this is pi times 0.005 squared times 10 is equal to pi times my r final squared times my length.
10.185.
Calculator.
But you can't do that in your head?
Do you want it in meters or centimeters?
Whichever one you give me.
That would be 0.00495 meters.
Everyone else get the same thing?
Yeah, I kinda crashed it. So multiplied, am I doing this right? So far, this is, for the initial, for the,
The left-hand side?
yes.
You can drop down to 5
Yeah, and that should be the left-hand side value.
Yeah, it's in micrometers. I don't know if, cause that's -6.
Yeah, you just, and then, well, you have that number and then divide by pi and divide by 10.185 and then take the square root.
Well, I think I messed up. I think I just canceled pi's because.
You can do that too. He had taken pi into account already, I think.
Yes.
Yeah,
Or-
or you could have just canceled out pi and not worried about it.
Oh, okay.
But,
Yeah.
you know, if you have pi on the left-hand side, you make sure you have pi on the right-hand side.
Yeah, I didn't, think of that, so that's,
Did you square it?
You didn't,
0.005.
Yeah.
Oh,
0.005
Probably written something like
times
that.
10 divided by 10.185.
did you square root at the end there?
what?
It's on there.
Oh, I didn't use the square root at all.
Yeah.
You have to.
You got his?
Yeah,
Okay. Someone believes in you, Thomas.
you have to, where you at?
But the lesson here, from my point of view, is
You're right. Yeah, that's what I did wrong. Yeah.
make sure you show your work on a test or quiz. And my experience is it's usually not an issue with 133. 110 is really a problem with people showing their work.
Is that
Like-
high schoolers?
No, it's conceptual physics.
Oh, okay.
Where did you get the 10? Or 6?
That's because I did it in the calculator and,
That's still there.
Yeah, that's what I got too.
All right.
What I didn't do the square root.
Yeah, all right.
So,
So, my transverse, so I start out with it being a diameter of this.
Then you divide that by the 10.185.
It has shrunk. Remember, this is the change in the radius here, so we can either do
I
the
can't
change in
quite
diameter over
understand
the
it.
diameter, or
By the
if we
10.185
cut it in half, change in radius over the radius,
on the other.
one or the other. So this puts it at, my change in radius was
Oh,
0.0,
okay.
so this is 0.0005
Yeah,
2.5
over
negative 5.
point
no, I got 77.01.
Yeah.
I think I'm behind now.
Oh. I'll help you on that. If I pass it.
The desk is still there.
It is.
There is a mistake written on the board. I left something off. It takes place in this region right here. This is not an intentional mistake, but let's use it as a teachable moment. What is the mistake in my transverse strain?
isn't there a negative?
Yes, it is. Because it was 0.005 and then it got smaller by 500 thousandths.
100,000,
So now, back to my Poisson ratio, which is my negative of my transverse strain over my longitudinal strain. So negative 0.01, negative. So that should be negative there. Over 0.0185.
yeah. 1541.
Units?
Well, there's always unit list, so. And it's also a ratio. It is also a ratio, so.
Yep. All right, so. Oh, questions up to here before I sort of wrap this bit up?
None here.
If you see me doing this, I'm counting at least 3 seconds just to make sure that people have a chance. If I ever go on too fast, feel free to jump back and say, wait a second, I saw the question. All right, now the assumption, when we got to it, I said this was a questionable assumption. The volume being the same assumes that the bonds between the atoms basically stay the same length. And so the distance between the atoms always stays the same. And that's not a valid assumption. That the final volume is not the same as the initial volume. And so it turns out that that Poisson's ratio, actually there are limits and there's a proof for it. It should never be bigger than 0.5. We're just a little bit above 0.5. If we had taken more significant figures, then it would have been closer to 0.5, but still not. I had calculated out just it's like 0.50 something. And Poisson's ratio will always, the lowest it can be is -1. Now, in terms of realism, I do have numbers here. Rubber is 0.5. That's at the maximum. Cheese is 0.45. Copper and steel typically 0.3, aluminum 0.35, concrete 0.2, cork 0. Most steels are in that mid-range, somewhere around 0.3, 0.2, 0.3. All right. Now, what would it mean, though, for a negative? If I have a material and I have a negative Poisson ratio, what does that mean in terms of the material?
It would expand as it stretches?
Yes. What is an example of something that expands when it stretches?
I don't know.
I still
Or theoretically, I mean, there's a children's toy out there that does it. Children's toy, adult toy.
Oh, the finger, finger trap.
Oh, that gets skinnier in the middle.
Oh wait, no.
I was
Yeah,
thinking of
that's
the
right.
ball.
What was that?
The ball.
The ball. Oh, the Huberman sphere. Yeah, it starts out like this, and then you sort of throw it up, and the thing
Yeah.
runs out like that. What's happening in that particular case, or more generally, if I have a material with sort of a structure like hourglass structure like that, as I pull on it, these sides come out like that, and it is, so the outside, so this expands this way, yes, this thing stretches that way.
Oh, now it makes,
It's
now
more
it
like
makes
a
sense.
mechanical thing than a material thing, though.
That's quite possible. I'm looking down here and, yeah, the example I said, for example, special foams and mostly from manufactured materials, so it does seem to be sort of on the man-made as opposed to nature. But it's possible there's some bizarre exception out there. And probably more likely, there's a possible exception that someone's claimed. All right. I think at this point, let's take a break. Stretch legs. 5 minutes.
Table's still there.
Knocking the table around.
My Google Home.
I tried to see the cashier's open, but I don't know if I have enough time to.
9:45.
Talk to them.
Yeah, I have no idea what kind of line there's gonna be today. I've gone in, I've had situations where I've been in and out and it's been easy, and then situations where I've waited in line for a half hour.
Gotcha. Cause I just wanna make sure I can take, 'cause I'm on my final semester and I'd hate to be forced to drag this out because of a fluke in their system.
Yeah. All right, so